Hello everyone! Today I am going to be doing an exercise out of Stephen Abbott's book, Understanding Analysis. And I'm going to do one of the first exercises. This is going to be exercise 1.2.2, which asks to show that there is no rational number r satisfying 2 to the r equals 3. So essentially we're going to show there is no rational number r satisfying 2 to the r equals 3. Okay, so that's what we're going to try and do here today. So really quickly, it's going to be useful to remind ourselves, obviously, the definition of a rational number. So we know that r must be equal to some integer p over another integer q. So p and q are both part of the integers. And we also know that q cannot be equal to 0 because we cannot divide by 0. So r is a rational number if it can be set equal to some integer p over some other integer q, and q is not 0. So that's just some review on the definition of a rational number. And we're going to try and show that r cannot be a rational number. So we'll try and do that. All right. Basically what I'm going to do is I'm going to do a proof by contradiction. So what that means is I'm going to have a list of steps that are going to go like this. And we're going to do all algebraically valid steps. So we're going to say, okay, this step is valid, and this step is valid, and this step is valid. And so we're going to go from a starting equation. We're going to go from some start to some finish. And we're going to have every step along the way be valid except for the first one. This one's going to be in question. And the first step is assuming that there is some rational number r that satisfies this equation. So we're going to assume that 2 to the r equals 3 for some rational number r. And then we're going to do a series of logical and correct steps and arrive at something. And if what we arrive at cannot be true, if we arrive at a contradiction, something that can't possibly be true, well, we know that a series of mathematically sound steps cannot conclude in a contradiction unless one of the steps is wrong. And because every step along the way we know is right except for the first one that's in question, therefore we can conclude that if the finish has a contradiction, then this starting assumption was wrong. So the starting assumption I'm going to make is that 2 to the r equals 3 for some rational number r. So I'm going to assume 2 to the r equals 3, where r is equal to p over q. P and q are both integers, and q is not equal to 0. So that's my assumption, and then we're going to do a series of logical algebraic steps from here. All right, so the first thing that I did in my proof is I took the log base 2 of both sides of this equation here. So I'm going to take this equation here, and I'm going to say log base 2 of 2 to the r is equal to log base 2 of 3. Okay, log base 2 of 2 to the r is just r, and then we get that r is equal to log base 2 of 3. Okay, so I think we all agree that these are valid algebraic steps. We can take the log of both sides of the equation, and log base 2 is just asking, well, what do I raise 2 to get this value? And the value that we input is 2 to the r, and so to get that value you would raise 2 to the r power. So I think we all understand that. Now at this point I'm going to go ahead and plug in our definition of r, that r is equal to p over q. So now I'm just going to say that p over q is equal to log base 2 of 3. At this point I'm going to multiply both sides by q. And when I do that, what I'm going to see is that we get p is equal to q times log base 2 of 3. Now you'll remember one of the properties of logarithms is that if you have a multiplicative constant outside of this logarithm, like this q here, you can actually bring it in as an exponent to the argument of your logarithm. So that's what I'm going to do in this next step. I'm going to say this is the same as saying p is equal to log base 2 3 to the q. Okay, cool. Now in this next step, what I'm going to do is I'm going to take, I'm going to exponentiate both sides with a base of 2. So essentially I'm going to put a 2 down here on both sides, but I'll show it in another step. So I'm going to say this is the same thing as 2 to the p is equal to 2 to the log base 2 of 3 to the q. Okay? Now we know, once again, that if we have a log base 2 here in the exponent, and we have a 2 as the base, that those can cancel, and so that we get the expression 2p is equal to 3 to the q. So essentially these two cancel and we just get this argument. And at this point, we have something where we're going to be able to kind of work some logical magic and try and get a contradiction here. So I hope you'll agree that all the steps so far have been decent and mathematically sound. One thing that I want to point out is that 2 to the p, we can write 2 to the p is equal to 2 times 2 to the p minus 1, right? I can just factor out a 2, essentially. Because 2 to the p, let's say p was equal to like 3, that would be like 2 times 2 times 2, right? Which is equal to 2 cubed, or which is also equal to 2 to the 3, sorry, 2 times 2 to the 3 minus 1, right? Which is equal to 2 times 2 squared. So I'm essentially factoring out 1, 2 here. And that's what I did. So I said, all right, well, 2 to the p is really equal to 2 times 2 to the p minus 1. And because this is equal to this, we can say that it's also equal to 3 to the q by the statement above. Now I'm going to go ahead and divide both sides of this equation by 2. So I'm going to get 2 to the p minus 1 is equal to 3 to the q over 2. And here is where our contradiction comes into place. This expression right here is a contradiction. And it's a contradiction because we said, we'll recall that p and q are both part of the integers. They're both part of the integers. And so what we're going to notice here is that if p and q are both part of the integers, I think you'll agree that if p is part of the integers, then that implies that p minus 1 is also part of the integers, right? I think that's pretty clear to see. So therefore, this is 2 raised to an integer exponent. So the left-hand side, we have 2 raised to an integer exponent. And if we have 2 raised to an integer exponent, that can only produce another integer, right? We're going to get a series of 2 times 2 times 2 times 2 times 2. And we're going to get a integer, but more importantly, we're going to get a even integer, right? Because when you multiply even numbers together repeatedly, you can only get even numbers. So on the left-hand side, we're going to get an even integer. And then on the right-hand side, here we have 3 to the q. Okay, so essentially remember q is another integer, but essentially we're multiplying 3 by itself a bunch of times. So we're multiplying an odd number times an odd number times an odd number, ... right? So we're doing this pattern on the right-hand side. And I think you'll see that if you keep multiplying odd numbers by each other, you will never reach a even number, because an even number requires some even number to be in this chain of multiplication, right? So let's say I multiplied this by 2. Well, now it's even, because 2 is an even number, and I can divide everything by 2, making it even. Or if I multiplied it by 8, right? 8 is an even number. It's divisible by 2. But the problem is that if you multiply all odd numbers together, you're only going to get an odd number. To have an even number, you need to have at least one even number in the chain of multiplication, such that you can then divide by that, making it divisible by 2. So because we have a bunch of 3's multiplied together, we're going to get an odd number. So we have an even integer on the left-hand side is equal to an odd integer over 2. Okay, now an odd integer over 2. Well, we know that odd numbers are not divisible by 2 evenly. So we know that an odd integer over 2 is not in the integers. It's going to have a decimal. It's going to be it will be a rational number, but it will not be an integer, right? 3/2, 5/2, so on and so forth. An odd number divided by 2 is not an integer. So here, essentially, we're saying that in fact, it doesn't even matter that this is even. We're just saying that an integer is equal to a not integer, because that's what this is. This is not an integer. So that can't be true. An integer cannot be equal to something that's not an integer, and so we have reached a contradiction. So at this point, we would say here we now have a problem. And we need to go back and look at our steps. And when we look at all of our steps, we see that they are all sound, except for our first assumption, which we don't know if it's sound or not. And it turns out it is not sound. There is no rational number r such that 2 to the r equals 3. And we've proved this by contradiction through these steps. So I hope that was useful to some people. If not, it'll be useful for me to go back and review. That's mostly why I'm recording this. I do want to make one comment about this step in particular right here, where we pulled out the factor of 2. You might say, can you always do that? So remember, the range of p is going to be from negative, negative infinity, the least valued integer, to positive infinity, the most valued integer. But more importantly, what happens around 0? It's always good to investigate these things. And it turns out that, let's say you had p equal to 0, then 2 to the p would obviously just be equal to 1. And then if you pulled out a 2, you would get 2 times 2 to the 0 minus 1, which would be equal to 2 times 1 over 2. So that would work out. That would be just fine. You don't get any divided by zeros or anything there. So this step here, you should be a little bit suspicious about pulling out that 2 and making sure that it works around 0 and at the infinities and things like that. So always be a little skeptical. Always look into these steps and make sure they're completely logical. But yeah, so there we have it. That's proved.